All right, let's check out the next one. And we are going to go ahead and begin by factoring this one as well. I'll try to stick with the correct color scheme on this one. GCF in the numerator is 2, so we're going to factor out a 2. And we'll have 2 and then x minus 1. And the denominator factors into x plus 3 and x minus 1. Whoops, I don't know why I put x minus x. That should say x minus 1. And we're going to cancel out that factor of x minus 1. Cancel that, and we have 2 over x plus 3. All right, fantastic, fantastic. We want to know what happens as we approach a 1. Well, that's where the hole is. As we approach negative 3 from the right, negative 3 from the left, and just negative 3 in general. That's our vertical asymptote. And we want to know what happens as we approach infinity. Okay, here's the horizontal asymptote. This is the vertical asymptote, and this is the hole. Let's do it. If I want to know where the hole is, I could just cancel out the factor that created the hole in the first place and then plug in the forbidden x value. So I have 2 over, plugging in the 1 here, 1 plus 3, and that gives me 2 over 4, which of course is 1/2. Done, right? As we approach negative 3 from the right, we are going to have, and let me graph this one. I already have it typed in, I just have to activate it. Clear that out. Oops, let's go to a standard window. Zoom 6. There we go. As we approach negative 3 from the right, we're going up towards positive infinity. As we approach negative 3 from the left, we go down towards negative infinity. So as we approach negative 3 in general, they're not going to meet. Well, if it was infinity, then we could make the argument that it doesn't exist anyway. And now we get to the fun one. X approaches infinity. As x approaches infinity, let's see what happens. Well, I want to see where this function levels off, and this function seems to level off at the x-axis. Okay, remember the little shortcut I told you a minute ago, and we're gonna pull out that bag of tricks again. And we would say, let me grab this eraser here. I'm just going to cover up the insignificant things. And I say insignificant meaning if I plugged in very large values, they would be insignificant. Plugging in very large values and then subtracting 12 and minus 8 is irrelevant. All that's irrelevant. I'm looking at 2x squared over x squared. That's just 2. I'm just looking at a 2, okay? I'm looking at x squared over 4x squared. Let me get the angle right. That's just 1 over 4. Okay, let's go to this one. You might say, oh, I'm just looking at this. 2x over x squared. No, you're not. Okay, where's the greatest magnitude? What's the highest exponent you see? It's squared. Well, you need something comparable, mispronunciation of the word, but you need something comparable in the numerator. Well, I don't have any x squareds in the numerator. We'll put them there. I have 0x squareds in the numerator, and having 0x squared in the numerator means I have 0x squared over x squared. So for large values of x, we're going to have 0. We're going to have a y. We're going to cross the y-axis. Let me rephrase that. We're going to have a horizontal asymptote of 0. So for large values of x, the value of this function is going to get closer and closer to 0. And if that didn't click for you, that's okay. Let's go about it a different way. Let's go to the table and plug in values that are super duper close to infinity, which is not possible, but we're going to go for it anyway. So 10, oh, that's not too big. 100, 1,000, 10,000. Okay, 2 times 10 to the negative 4, that's 0.0001999. Okay, let's do this. Let's just get crazy with it. That is 0.0000000000199999999. Okay, we're getting super close to 0. And again, the reason why is I plug in large numbers for x. I'm going to ignore the 2, and the 3, and the 2x and the 2x. And all I'm left with is this x squared in the denominator and no similar term in the numerator to balance it out, to compare it with. And so I have 0x squared in the numerator. So 0 divided by 1 is just 0.